Two identical cars accelerate on a straight road. One speeds up from 10 to 20 miles per hour. The other speeds up from 50 to 60. Each gains exactly 10 miles per hour, yet the faster car gains almost 4 times as much energy of motion. That energy is kinetic energy, and it grows with the square of speed. In this video, we define it, compute how it changes, and uncover a result hiding inside ordinary one-dimensional kinematics. Force times displacement equals the change in kinetic energy. Kinetic energy is the energy of coherent motion, all the molecules of a body traveling together. The name comes from the Greek kinetikos, meaning moving. Set up the simplest case. A car of mass m on a straight road, with the x-axis laid along the road. For an observer at rest on the ground, the car's velocity is its x component, v sub x, times the unit vector I hat. The speed v is the magnitude of that x component. The kinetic energy k of a non-rotating body is defined as 1/2 mv squared. Mass is positive and the speed is squared, so k is a positive scalar, or 0 when the body is at rest. Check the units. Mass carries kilograms, speed squared carries meters squared per second squared. So kinetic energy carries kilogram meter squared per second squared, and that combination is defined as 1 joule, the unit of energy named for James Prescott Joule. Notice what the definition leaves out: direction. A car driving east at a given speed and an identical car driving west at the same speed have exactly the same kinetic energy because only the square of the speed enters. Kinetic energy is a scalar. Now let the car change its velocity. In the initial state, it moves with x component of velocity v sub xi. In the final state, at some later time, it moves with v sub xf. The change in kinetic energy is final minus initial. Delta k equals 1/2 mv sub f squared minus 1/2 mv sub I squared. Each term carries the square of a speed, so equal steps in speed do not produce equal steps in energy. Changing speed at high speed costs far more energy. That asymmetry is the point of our first example. Here is example 13.1. Car A increases its speed from 10 to 20 miles per hour. Car B increases its speed from 50 to 60 miles per hour. The two cars have the same mass. The first question, what is the ratio of car B's change in kinetic energy to car A's, and which car has the greater change? Write the ratio. Car B's change is 1/2 m times its final speed squared minus 1/2 m times its initial speed squared, and likewise for car A. The factor 1/2 m is common to every term, so it cancels, leaving pure speed differences. B's final speed squared minus B's initial speed squared over A's final speed squared minus A's initial speed squared. Substitute. 60 squared is 3,600. 50 squared is 2,500. The numerator is their difference, 1,100. 20 squared is 400. 10 squared is 100. So the denominator is 300. The ratio is 1,100 over 300, which is 11/3, about 3.7. Car B gains almost 4 times the kinetic energy of car A from the very same 10 mile per hour speed increase. The second question changes the observer. Watch the same two cars from a reference frame moving with the initial velocity of car A, 10 miles per hour. In that frame, every velocity drops by 10 miles per hour. Car A now accelerates from rest to 10 miles per hour. Car B now goes from 40 to 50. Run the same algebra. 50 squared minus 40 squared is 2,500 minus 1,600, 900. For car A, 10 squared minus 0 squared is 100. The ratio is 900 over 100, 9. Two things to notice. First, the ratio itself changed from 11/3 in the ground frame to 9 in the moving frame. Second, both cars show smaller kinetic energy gains in the new frame, Car B's numerator fell from 1100 to 900, and car A's from 300 to 100. Kinetic energy and the changes in kinetic energy are frame dependent. There is no contradiction. Observers in different frames measure different speeds, and energy is built from speed. So far, we computed energy changes from given speeds. Now connect them to kinematics, to what produces the speed change. Take a rigid body moving in one dimension, treat it as a point mass with constant acceleration. At time 0, it has velocity component v sub xi. If the acceleration points along the displacement, the body speeds up. If it points against the displacement, the body slows down. For constant acceleration, the displacement is delta x equals v sub xi times t, plus 1/2 a sub xt squared. Now the unusual move, multiply the acceleration by the displacement. The product a sub x times delta s looks arbitrary, but watch what it becomes. Evaluate the product. For constant acceleration, a sub s equals the change in velocity divided by the elapsed time. V sub xf minus V sub xi all over t. Substitute this for both factors of acceleration. The time t cancels everywhere, leaving two clean terms, the velocity difference times v sub xi plus 1/2 times the velocity difference squared. Expand each piece. The first term gives v sub xf times v sub xi minus v sub xi squared. The second gives 1/2 v sub xf squared minus v sub xf times v sub xi plus 1/2 v sub xi squared. Now add them. The cross terms cancel. The two v sub xi squared pieces combine into minus 1/2 v sub xi squared. What survives is 1/2 v sub xf squared minus 1/2 v sub xi squared. Acceleration times displacement equals the change in 1/2 the velocity squared. Pure kinematics. No forces yet. Their identity is kinematics. One multiplication turns it into physics. Multiply both sides by the mass m. The left side becomes ma sub s delta x. The right side becomes 1/2 mv sub xf squared minus 1/2 mv sub xi squared, exactly the final kinetic energy minus the initial kinetic energy. So ma sub x delta x equals k sub f minus k sub I. Now bring in Newton's second law, which in one dimension reads f sub x equals ma sub x. Substitute on the left. F sub x times delta x equals k sub f minus k sub I. Read it as a sentence. The force component along the motion times the displacement equals the change in kinetic energy. A force along the displacement raises the kinetic energy. A force against it lowers the kinetic energy. Newton's second law had energy inside it all along. Real accelerations are rarely constant. Suppose the acceleration varies along the path. The remedy is the standard move of calculus. Chop the displacement into n small intervals indexed by j running from 1 to n. Interval j covers displacement delta x sub j in time delta t sub j, and the velocity components at its beginning and end are v sub xj minus 1 and v sub xj. At the boundaries, the velocity at the start of the first interval is the initial velocity, and the velocity at the end of the last interval is the final velocity. Within one small interval, use the average acceleration. Our constant acceleration identity then applies interval by interval. The average acceleration on interval j times delta x sub j equals 1/2 v sub xj squared minus 1/2 v sub xj minus 1 squared. Now add the contributions of every interval. The sum over j from 1 to n of the average acceleration times delta x sub j. Write out the right-hand sides. The first interval gives 1/2 v1 squared minus 1/2 v0 squared. The second gives 1/2 v2 squared minus 1/2 v1 squared. The plus 1/2 v1 squared cancels the minus 1/2 v1 squared. The next pair cancels the same way, and so on down the line. every interior velocity appears once with a plus sign and once with a minus sign, the sum telescopes. Only the endpoints survive, and the whole sum collapses to 1/2 v sub xf squared minus 1/2 v sub xi squared, no matter how the acceleration varied along the way. Refine the chopping. Let n go to infinity and let every interval width delta x sub j shrink to 0. Both conditions must hold together. In that limit, the sum of average acceleration times displacement becomes, by definition, the definite integral of the acceleration with respect to position, taken from x sub I to x sub f. The right-hand side never changed. So the integral of a sub x with respect to x equals 1/2 v sub xf squared minus 1/2 v sub xi squared. Nothing extra went in. This follows from the definition of acceleration as the time derivative of velocity. Pause on what is new. You already know one integral of acceleration, the integral over time. Integrate a sub s with respect to t from the initial time to the final time, and you get the change in velocity, v sub xf minus v sub xi. That is the familiar kinematics result. The new result integrates the same acceleration with respect to position, and it produces something different, half the change of the velocity squared. Same acceleration, different variable of integration, and it is the position version that connects to energy. Repeat the multiplication that worked before. Multiply both sides by the mass. On the right, 1/2 mv sub xf squared minus 1/2 mv sub xi squared is the change in kinetic energy, k sub f minus k sub I. On the left, the mass slides inside, given the integral of ma sub x with respect to position. And by Newton's second law, ma sub x is the force component f sub x. Conclusion: the integral of f sub x with respect to x from the initial position to the final position equals the change in kinetic energy. For a point-like object, this is exact, and for an extended rigid body, it governs the center of mass, because the external force accelerates the center of mass. This position integral of force is the seed of the concept called work. Here is the chain we built. Kinetic energy is 1/2 mv squared, a positive scalar, measured in joules, blind to direction. Its changes grow with the square of speed, so identical speed gains cost very different energy, and the answer depends on the observer's reference frame, as the two cars showed. Then kinematics plus Newton's second law force the conclusion. For constant force, force times displacement equals the change in kinetic energy. For any force, the integral of force over position equals the change in kinetic energy. That position integral is about to receive its own name, work, and it is the doorway to everything that follows in energy physics. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.